Welcome to module 5 of the course Time Dependent Quantum Chemistry. In this module, we will go over the numerical approach to solve TDSE. That's the practical thing which we are going to learn for the first time in this course. Now, we have already understood in the first module that when a potential does not have any explicit dependence on time, so potential does not depend, and that's the way we have been assuming. There are problems in time dependent quantum chemistry where potential will be dependent on time, but that part will be discussed later. So far we are saying that the potential does not depend on time. If it doesn't have dependency on time, then one-dimensional Schrodinger equation should look like this. We are quite familiar with this form, and we can solve this equation with the help of variable separation method. We have used this variable separation method before, and in this method the eigenvector and corresponding eigenvalues of the quantum system before the onset of time evolution, they are called stationary states. We can get those eigen states and eigenvectors from this time independent Schrodinger equation. So the basic idea is that in order to solve this TDSE, we have to first get the stationary states and stationary state wave function and stationary state energies from the time independent Schrodinger equation, and that's the state before the onset of the time evolution. In this and we get a set of solutions. We have understood that. Think about particle in one-dimensional box. When you have solved the time independent Schrodinger equation, you have got multiple solutions like this way. Similarly, for any quantum system, its time independent Schrodinger equation will give you a set of solutions, and here n denotes the nth eigenstate. So n is the nth eigenstate, and once we get that solutions from here, we can get the time dependent eigenstates, which is nothing but multiplying the stationary states with the help of by this time dependent phase factor that we have understood, and as a general solution, which means that if the time evolution is going on between 0 to t time, so at any time t, let us say t1 time, within this time scale, within this time interval, let us say time evolution is going on. Within this time, at any time t, if I have to present the wave function, that will be presented by the linear combination of these states, and where Cn is the time dependent expansion coefficient, which will control what is the contribution of each of these functions to the total wave function, time evolving wave function. So that's the way we have seen variable separation method and its usage in time dependent in solving TDSE. But we have to remember that if the potential has an explicit dependence on time, if the potential is, let us say, Vxt, here instead of Vx we have, let us say, Vxt. In that case, variable separation method cannot be used anymore. In addition to that, so this is one concern we have. Second concern we have is that obtaining the solution to the TDSE via eigenvalues and eigenvectors may not be always practical. So, so if I want to get a solution of TDSE with the help of eigen values and eigenvector, in terms of that, it may not be practical because a very large number of states are needed, or because calculation of these states are too expensive. And in that case, it is convenient to compute the time evolution of a given initial state directly without making use of a large number of eigenstates. So variable separation method is a good idea, but it may not be practical all the time. So we need more general approach to solve this TDSE, and the general approach to solve this TDSE is to use the time evolution operator. This is called time evolution operator. This UT is representing the time evolution operator. What it does, it is actually we start from an initial state which is psi x0, that is at t equals 0. What is the state is? This is t equals 0 state at the initial state, and then we monitor the system as a function of time with the help of this time evolution operator, which is an exponential operator. And in this module, we will find out what are the properties of this time evolution operator, and how numerically one can implement this idea, so that using Python programming one can find out at different time how the wave function is evolving. Once we know the wave function at a particular time, we will be able to find out its average position and many experimental observables. We remind here that this form, this time evolution operator, this form, that this is a general solution of TDSE actually. We in the last module, in module 4, we have seen that how we have got this expression for the time evolution operator. So let's proceed, and we will, before we represent the numerical implementation of time evolution operator, we will go over the general properties, some of the general properties of time evolution operator, because that will help us understand the meaning of this time evolution operator. Different properties will help us understand, or numerical implementation also will be much easier to do once we understand the meaning of this expression. So this expression following, I have psi xt, any time I would like to find out the wave function, that can be done if I know the initial wave function and then employ one time evolution operator on it. This is the time evolution operator. So the first property of time evolution operator is that this u t equals e to the power minus I is called time propagator because it propagates the wave function in time. So if I know the wave function, if the initial wave function that is at t equals 0, if initial wave function is known and its Hamiltonian is also known, if both are known, then one can find out the wave function at any later time. So that's what it means. This is an exponential operator, and we have already seen that in chapter in the previous module, module 4, we have seen that this equation psi x t equals e to the power minus I h cut t by psi x 0. This equation comes from as a solution of to the TDSE, because remember at some point we said that this operator is equivalent to age, and this part came from TDSE in the derivation, and that has been explicitly shown in module 4. This is an exponential operator, and because it's an exponential operator, it has to be expressed using a Taylor series expansion, which we have used already in module 4, but here we are just mentioning to collect all the general properties. So how do I express this exponential operator? This is going to be nothing but summation of m equals 0 to infinity minus I h t by h cut divided by m factorial, which is nothing but 1 plus minus I h t by h cut plus 1 by 2 minus I h t by h cut whole square, like this. I have infinite terms. So that's the way we are going to express this exponential operator. Time evolution operator is reversible in time, and this reversibility is a unique property in quantum mechanics. We'll prove that how it is reversible. If I consider delta t time advancement, then that has to be written as minus I h by h cut, and if I want to go back in time, then it is going to be minus delta t, and that's going to be I h delta t by h cut. So if I try to evaluate what will happen if I first go back and then come back acting on psi x0. So I am just taking the product of these two time evolution operators. If I do that, then I'll be able to get I h cut delta t by multiplied by e to the power minus I h delta t by h cut psi x0. That is nothing but psi x0. So what it suggests that first I am making an time advancement. Then what I get, I am making one backward propagation in time. So one forward propagation, one backward propagation, in the end giving me back this wave function. That's why it is reversible in time. This is quite different from our real life experience. In real life experience, we cannot go back in time. We have to always move forward. But here, I can go back in quantum mechanics with the help of this time evolution operator. I can go back in time. So my system will again evolve to the initial state. Time evolution operator is an unitary operator, which means that I'll be able to write down, I'll prove it, but before I prove that, I'll be able to write down this expression, this equality. Inverse is going to be equal to its adjoint. That's the definition of unitary operator, which we have seen in module 4 in the previous module. So what it means, it's inverse is equal to its adjoint. So we'll prove that. One can prove it very easily. If I try to find out e to the power minus I h t by h cut inverse, that is going to be e to the power I h t by h cut, which can be written as with the help of Taylor series expansion, we will be able to write down 1 plus I h cap t by h cut plus half I h cap t by h cut whole square plus like this. We'll be able to write down this inverse of this operator. Now here I mention one important thing. This is nothing but 1, but we are giving with a cap to show that the entire addition, entire term is representing an operator. So this is an 1 operator. 1 operator is nothing but multiply by 1. And to make the notation correct here, every term we have made to be an operator. That's why we are giving this cap. Otherwise, it's just 1. So we will now look at the adjoint. How does it look like? E to the power minus I h cap t by h cut. Its adjoint. Its adjoint is going to be 1 plus minus I h cap t by h cut plus half minus I h cap t by h cut whole square plus like this. So entire term I have to consider adjoint, and we have learned from the previous module that if I make adjoint, it is going to be 1 plus adjoint is going to be H adjoint T by H cut plus half I H adjoint T by H cut whole square, like this. And because H is an Hermitian operator, H is an Hermitian operator, H is actually an Hermitian operator. So I can write down it is self adjoint, which means that it will be equal. So this term, this adjoint sign will go away because they are equal, and the moment it goes away, this term and what I have got here, this term, are equal. That's why this equality holds. So unitary time evolution operator is an unitary operator. We'll see that we have been saying in many occasions in this course that for the to explore quantum dynamics, we need to have wave function which is normalized initially, and it will remain normalized over all the time when we are exploring the quantum dynamics, and that is called norm preserving. So first thing we have to check, because we are evolving time, we are monitoring the evolution of wave function in time, we have to understand that whether when I employ this unitary operator on this function, whether I am preserving the norm or not. That is most important part of quantum dynamics before exploring quantum dynamics. So we'll check it first. So we'll see that if psi xt is represented as e to the power minus I t by h cut psi x0, then I can consider its absolute value square of its absolute value, that is going to be e to the power plus I by h cut multiplied to the power minus I h cap t by h cut, then psi x0, that is nothing but psi x0. So what we see is that it's at t equals 0, its norm, and at t equals t time, any time t, any arbitrary time t during the time evolution, its norm is going to be equal. So that is why we can say this is a norm preserving. We can explicitly prove it as follows. Norm are represented by these double lines, vertical lines, which is nothing but, we have seen the definition of norm in the previous module, that is nothing but psi star xt psi xt dx to the power half. That's the norm, definition of the norm. Now I employ time evolution here, so that's going to be e to the power I h cap t by h cut psi star x0. Here I have removed this negative sign because this is of complex conjugate part of the wave function. So this part is represented here, and then other part will be represented as 1 minus I h cap t by h cut psi x0 dx to the power half. So I will rewrite little bit mathematical trick will help me get to the point we are trying to make here. E to the power minus I h by h cut psi x0. The entire thing I have clubbed them together and then placed it under this star, which means that entire thing has to be complex conjugate of this term, and then remaining part I am keeping it here, I h t by h cut psi x0 dx to the power half. So this is I can write down, because I can take the adjoint. So if I take the adjoint of this, so it's going to be minus infinity to plus infinity e to the power I h t by h cut e to the power minus I h t by h cut psi x0 star psi x0 dx to the power half. So this is nothing but I have now psi x0 star psi x0 minus infinity to plus infinity So we are using making use of unitarity property of the propagator. So what is going on? Its norm is preserved because it is an unitary operator. And which step we have used this unitary property? In this step. You see, this term has been taken here. How did we get that? Because we said that this we have proved that this time evolution operator, inverse of the time evolution operator, is actually its adjoint. And adjoint, the definition of adjoint, being an adjoint, I can take this operator from here to the other side, and if we take that, then that is going to be inverse of that operator, and that's exactly we have taken. This part and this part is inverse of one another. And so because it's an unitary operator, its norm is preserving. So that's something which we should remember. So as a result, normalization constant does not change during dynamical evolution of the quantum system. So these are the 5 properties we have shown so far, and we will stop here, and we will present the numerical implementation of time evolution operator in the next session.